All right, so we're going to start what will be your next module, which is troubleshooting, refrigeration troubleshooting. So if you go to your Blackboard, this will be found in Module 6, which is refrigeration troubleshooting. And right now, all I have in there is two labs, but this video will go in there as well. So should be able to access that. I'll be probably downloading some more information as well, some more troubleshooting guides and things like that. So there'll be more added to that than what you see on my screen. Once you're in there, you can go ahead and click on one of those labs. And so I'm actually going to open up one of those 6A, which is refrigeration and airflow. So if you haven't watched the one that walks you through how to find superheat subcooling, you're going to want to go watch that first. But if you have watched that and you feel kind of comfortable with at least understanding what it is and how to measure it, then we're going to show how that you would use that to troubleshoot along with your pressures and delta as well, temperature. So what you should start understanding at this point is how the system is starting to work as a whole together, that each part affects everything in essence. So as long as everything's working as it should work, you should run, your pressure should be where you want them, your superheat, your subcooling should be where you want it, your airflow should be good, your delta, your temperature, your supply coming in should be good, your temperature split across it should be good. But what if it's not? So this is where your troubleshooting kind of kicks in a little bit. And actually in 250, which is your cooling dehumidification class, we'll get into this a little bit more. But I just wanted to kind of build this lab that sort of introduces you to troubleshooting, at least in a controlled setting. So you're going to go through these labs and you're going to actually make these problems happen, and then you're going to see how the system reacts. So it's not like I'm creating something that's going to trip you up. You're creating all the issues. So I want to walk you through these labs, and by walking you through the labs, kind of give you a little heads up about some of the details of the lab and the material in them. All right, so you'll notice on both of these labs, both 6A and 6B, 6A is going to be more concerned with refrigeration and how airflow affects it, and then B is going to be how charge affects it, meaning how much refrigerant's in the system. So, excuse me, allergies. So you'll see this chart. You'll notice that it's broken down, and there's different versions of this chart you can find. I just found this online. Fixed metering and TXV systems. So depending on the type of metering device you have, some of these may be the same and some of these will be a little bit different. The TXV, we haven't really gotten into the nuts and bolts. That's more in your 250, where we really dig into like different types of metering devices and how they work and that sort of thing. But for now, just imagine that a fixed piston or a fixed metering device is just a certain size, and that's all that it can be. But a TXV is an expansion valve, which means it opens and closes, widens and closes off that based on demand. And so there's some ways that measures that demand. And we'll, like I said, we're not going to get into that too much in this class, but it's going to open and close to allow a certain amount of refrigerant in. The main thing that a TXV does is it tries to maintain superheat. So it's kind of, some people will call it a constant superheat valve, to where its job is to try to maintain optimal superheat conditions, even if everything else is kind of going awry. So you may see on here a lot of times that where it may talk about low charge or overcharge or something else, that it might say that it would be normal, whereas if it were compared to a fixed, so like here, this example here, sorry, up here, low charge, overcharge, gives you arrows, but down here, low charge or overcharge, it gives you normal. So what that TXV is going to do is it's going to try to open and close to maintain a constant superheat, because it knows that if we maintain a constant superheat, then we're maintaining a constant flow of liquid refrigerant to the evaporator. And so if it can allow more in and still do that, then that coil can do the maximum amount of work it's supposed to do. And the same thing if it's overcharged. If it's overcharged, it can just close down a little bit and allow less in to try to maintain that constant 8 to 12 degree superheat that it wants. Doesn't mean it's always going to do that. And it also doesn't mean that you shouldn't check superheat on a TXV system, but you shouldn't charge a system based on superheat alone if it's a TXV, because that TXV is going to open and close. And so really there's, it should be normal unless something's way out of whack. So I always like to check it, but I don't use that as my big test. So what does all this mean? Well, I've got another paper that I'm probably going to hand you that you can keep in your record that kind of has something similar to this. So it goes through different scenarios and how each one of those scenarios would impact pressures, temperatures, subcooling, superheat, amperage, delta T. But I thought this one was pretty good and pretty easy to read. So probably your most common faults, especially at this point, we're not going to get into anything that's super rare or complicated. Probably your most common issues that are refrigeration issues, not necessarily electrical issues, even though they could be because of an electrical problem. Your most common ones are going to be charge related, which means you either got too much refrigerant or not enough. More common is not enough because the system develops a leak, or because it's been worked on every 6 months for the last 2 or 3 years, and they haven't properly put the refrigerant back in the system when they take the gauges off. Maybe they've lost some that way. So what we're going to try to find out is what a low charge system looks like, what an overcharged system looks like, what low indoor airflow looks like. So dirty filter, dirty coil, poor bad fan, your blower kills out, liquid line restriction. I'm not going to dig into that one too much because that one can get a little bit weird. And then, because actually it even says down here it's got an asterisk beside it. So oversized piston, obviously, unless if it's worked right and then all of a sudden it starts not working right, chances are it's not that. But I guess that's what it would look like. And high ambient, I'm assuming that's what they mean by RA. Return air, the high return air temperature. So this would be like increased load. So it's really hot in the house. So what's that going to do? All right. So first of all, let's go back to this this picture. These pictures. All right. So this is your basic circuit. So you've got a couple of different visualizations of that. All right. So if you're looking, let's look at this picture. Actually, I kind of like this one. So your evaporator is what's doing all the work. So superheat, first of all, is measured in the evaporator, which is in the low side. So whenever we get in class, I'll actually draw this on the board, probably help a little bit. But if you're looking at this unit here, the air handler, superheat, even though you would think it would be on the hot side, is actually on the low side or the cold side. So this always throws people because they think superheating occurs outside because that's where the high pressure is. But you got to think about what's going on inside of the system, not what's hot or what's cold, because remember, everything's relative. So refrigerant enters the evaporator through the TXV or through the piston, and it meters, and it causes a high pressure liquid coming in to turn to a low pressure liquid vapor mix. So that liquid vapor mix comes through the evaporator and starts to pick up heat as long as there's air blowing across it. So if it's picking up heat, then that heat gets transferred from the air to the refrigerant, and as a result, the refrigerant boils or it starts to evaporate, so it becomes vapor. It's still cold. We've talked about in class before, feel that line's cold. It's really hard to believe that a cold line can hold all that heat, but as we've mentioned in class, that just shows you the capacity that refrigerant has just by changing states. So even though that line can be so cold it's sweating, it can be 50 degrees, it still has all the heat because it went through that latent change. So what we're really trying to do and what we're trying to measure with superheat is how much of this evaporator is actually going through that latent change of evaporation. And then the subcooling is going to do the same thing on the condensing side. So if you understand superheat, you'll understand subcooling. So superheat is just saying how much of this coil is full. So kind of a basic rule of thumb. I know rule of thumbs are dangerous, but a basic rule of thumb is you want to keep 8 to 12 degrees of superheat. That's kind of just a good guideline. So what is the purpose of superheating refrigerant? Well, first of all, what is it? It's actually heating the refrigerant, adding more heat to the refrigerant beyond the point that it is completely vapor. So the evaporator is changing that refrigerant from a liquid to a vapor until it becomes 100% vapor. So here on this picture at 0.16, this 0.16 would be the point at which it becomes vapor. Now, once it becomes vapor, the latent change is gone. So that's where the latent change stops. And so what we've mentioned in the past is that you can't latent and sensibly change something at the same time. So it's either latent or sensible. So from the time it leaves the TXV until it completely vaporizes, that's all latent. That's what's doing all the work, because that's the evaporating process, the evaporation process. So that's where we're picking up all that heat. That's what has all that capacity to grab all that heat and capture it just through the changing of state. And so as a result, the air coming out the top is going to be colder. And that's what we've said in class before is like, if you want a visualization of how much capacity that cold line of vapor refrigerant actually has, feel the difference between your room temperature and the supply temperature. You got 20 degrees temperature drop from your whole house, and it's all being captured in this line that seems to be very cold, but it's all because of the latent. So that latent change happens until that completely evaporates. Once it completely evaporates, everything beyond that point is known as superheat. So what you're doing is you're heating it up to the point that it's vapor, and then you're heating it up a little bit more. So at this point, the latent is done, which means now we're sensibly heating again. So if you could imagine boiling a pot of water and you were, maybe able to capture that steam. Once you boil off all the liquid and you stop the boiling process, all that latent is gone. And now at this point, all the heat that you're adding to that vapor in that container would be superheat. It would be the same for steam. You can superheat steam just the same way. So it's just additional heat beyond the saturation point, or additional heat beyond 100% vapor. That's superheat. Even though it's cold, it's superheated, which means it has more heat than it needed to actually convert that to 100% vapor. So if you had a system that had 0 degrees superheat, what that would mean is, or 1 degree or whatever, that would mean that this coil were completely full of liquid, or not completely full, but it had evaporating liquid all the way to the end. So how do we measure superheat? Well, normally we measure it. There's a few different ways you can measure it. Most accurately to measure the evaporator would actually be here where this bulb is strapped here at 0.18. But normally we measure it outside. We measure it on the vapor line. So we've got our gauges hooked up there, and then you'll be here at like 0.19 on this picture. And you're going to just put a temperature clamp on that line. And then you're going to measure the temperature of the line, and that's going to give you some sort of superheat reading. So I guess a question that I would ask you to think about is superheat latent or sensible? Well, we've already said that it happens after the latent change stops. So if it happens after that and it's additional heat added after that, then it's sensible. Well, if it's sensible, it's measurable with a thermometer. And if it's measured with a thermometer, then that means it is just degrees. So if that, if the saturation point of your refrigerant, and this is what you're reading with your gauges. So your gauges are saying, indoor minus 30, for example. 70 in the house, 40 degree saturation temp. That's this point right here, number 16. That's your saturation point. So that's what your gauges are reading, is that saturation point. Think back to the, no matter how full or empty this thing is, it's going to read that point. That's exactly what it does in your refrigerant jug. When we measure that in class, no matter how full or empty it was, as long as there was liquid and vapor present, it was going to read the same thing based on its temperature. So this number 16 here is where it becomes completely vapor, and then we're just going to add additional heat, 8 to 14 degrees, kind of as a starting point, would be a good range. And so that means that in addition to 100% vapor, we're going to put in a little bit of superheat, which serves a couple of different purposes. One of the purposes is it protects the compressor. So the compressor, as we've already discussed, cannot or should not see liquid. If it does, that's going to create a problem. or it could create a problem over time. So it's going to be, bearing washout. It's going to wash out the oil. You could also just damage the parts just by dumping liquid into it. So you really want to limit that liquid exposure to that compressor. So superheat provides kind of a safety net or an insurance that compressor is not seeing any liquid. So even if I were able to get this coil completely full, that would be better for efficiency, because that would mean all of my coils doing work. But your system's going to be sized to allow for this superheat anyway. So you've got this extra percentage, and I don't know how much of your coil it'll be, but I'd say it's the last couple of passes through those coils. Maybe the last 5 to 10% is going to be superheat. Superheated vapor doesn't have much capacity to pick up any heat. At this point, its only job is just to make sure that you're not getting any extra liquid to the compressor. That's the main point of superheat. So you just want to make sure that you're done evaporating before you send it out of the evaporator and into the compressor. So that measures that we have that safety net in place. Now, if it's an insurance policy and if it's a safety net, why not have more? Why stop it at 8 to 12, 8 to 14? Well, because superheat is also a measurement of how full this evaporator is. So what we're trying to do is to find this perfect balance of efficiency and performance and also protecting the compressor. So that stopping point where it becomes 100% vapor, I want that as late in the game as I can get it safely. So you would think, well, why not have it halfway down? That way you're not going to damage your compressor. Yeah, that's true. But if the majority of the coil has to be going through that latent change to do the job, and it's not, then you're going to, that's going to show up there. You're going to, be losing capacity. So it may work fine if it's 80 degrees outside and, not too hot in the house. But once it gets hot in the house and it's hot outside, now you need all of that coil to do this work, and you don't have it all available. So that's where your charge comes in, for example. So we need it to be there, but we don't need it to be the most of the coil does not need to be doing that, because at this point, that part doesn't do a lot of work. Think back to our water bottle lab, to where we had the one that was frozen, that was thawed, and then we had the other one that was already thawed, but it was cold. They both did work and they both attracted heat, but the one that was going through the latent attracted way more than the one that was in the sensible. The one that was already water, 100% water, even though it was cold, it didn't pick up near as much heat. So sensible heat just doesn't have a lot of ability to catch heat, but it is necessary. So we add that 8 to 14 degree window that makes sure that our compressor does not flood. We don't get liquid flow back. Okay, at that point, your compressor compresses that and sends it through the condenser. It goes into the condenser as 100% hot gas, which means it is 100% vapor. And at this point, it is still superheated, and it's very superheated because you're taking a low pressure superheated gas and you're heating it more and you're raising its pressure. So now, you're going to have a highly superheated gas. So in the evaporator, we already, once it comes to the evaporator, it was already in the process of breaking down because of the metering device. In the condenser, you actually don't have anything that starts that process other than just blowing a fan across it and removing heat. So in the condenser, the first thing that actually happens, and you may see this on a test, the first thing that actually happens is what we call de-superheating. So if I superheated it, and superheat is all sensible, before I can ever start to condense, condensing being all latent, I have to remove the superheat. So that's another reason why you don't want additional superheat collected in the evaporator, because once you compress that makes more discharge superheat, which means more of my condenser is going to be used to get rid of that extra superheat. So that means less of my coil is actually going to be used to condense and remove heat from the system. So, like I said before, it's all tied together. So if I put more of sensible heat in on the evaporator side than I need, I've got to get rid of that on the condenser side. So I want to stay as close to that saturation point as I can, but still make sure that my compressor is safe. So the first thing you do in a condenser, the first step is de-superheating. So if we have, and I'm just making up a number here, but let's say it's 40 degrees discharge superheat. So let's say, the line is 140 degrees and my condensing temperature is 100. So let's say that it's 140 degrees. I'm just making that up. If I got to remove 40 degrees, then that means I have to remove 40 degrees of sensible heat before I can ever start to condense. Remember, I don't do any work really through the latent or through the sensible. So I have to get to that latent as quick as I can, because that's the thing that's going to really start the work. So in that condenser, as soon as it desuperheats, it's going to start to condense. Well, condensing means it gives up enough heat that it starts to change back from a vapor to a liquid. So it meets its saturation point on the way down, and it becomes a liquid. It just becomes more and more and more and more liquid and less and less and less vapor until it is 100% liquid. At that point, it is 100% liquid and a little bit more. Why would I need a little bit more? Kind of the same reason I needed more superheat, to make sure that the compressor didn't get vapor feedback. The TXV or piston needs a solid stream of liquid. So remember, in class we talked about the little spray bottle, and if you turn it upside down and it's going to suck air. It's kind of the same way with this. So it has to have a steady stream of liquid to operate properly. So this is what we call subcooling. So why do we call it subcooling? Well, because we are cooling this refrigerant to the point that it will become liquid. And then once it becomes liquid, we cool it just a little bit more below that. So subcooling, cooling below the additional heat that is removed from a system beyond its saturation point back to liquid. So once it becomes 100% liquid, it goes to the TXV and it does it all over again. All right, so that's kind of a review on how it should work. What happens if it doesn't? So what are some indications that maybe I've got an issue? So this lab is lab 1 or lab A, 6A, talks about airflow. So what would happen if I lost a fan outside? So my fan stops running. Is that going to affect superheat or subcooling or both? Actually, it's going to affect both. It's going to affect the compressor's ability to remove heat, or the condenser's ability, sorry, to remove heat. So let's go over here to our, let's see. All right, let's look at this. So look at dirty condenser. So it doesn't say like bad fan, just a dirty condenser. But either way, it's poor condenser airflow. So what would be the symptoms of poor condenser airflow? Well, according to this, my suction pressure would be high, head pressure would be high, superheat would be low to normal. This is on a fixed. Subcooling would be low to normal, and your amperage would go up on your compressor, which we're not into that yet, and your delta would go down. All right, so let's with that in mind, you can pause this right now if you need to write that down or whatever, and let's go back to this picture. So right here, you see your compressor running. You see, the condenser pulling air out. Well, if that outdoor fan were to stop, what all is going to be affected by that? And maybe most importantly, what's going to be the first sign that that's a problem? Is it going to affect the high side or the low side more and quicker? It's going to affect the high side most, because that's where it's directly affecting it. Now, ultimately, it will impact the low side performance as well, but it's immediately going to affect the high side. So how's it going to affect it? Well, a few different ways. First thing it's going to do is it's going to stop the ability for this condenser to condense. So if it can't condense, then what also can it do? I mean, what does condensing allow us to do? The condensing process allows us to remove heat. So if I'm not pulling air across it, then I can't remove heat very well. So I don't have colder air coming across this hotter coil. So now all this heat that I captured in the house is getting pumped to this outdoor unit, but the problem is that outdoor fan is stopped. So the indoor unit's working like it's supposed to, and it's saying, hey, we're just picking up heat, we're sending it outside for you to get rid of it. And the outdoor fan stops, so there's no way for it to get rid of it. Well, if the fan is what causes this refrigerant to condense, and the condensing is what allows us to remove heat, if the fan stops, the refrigerant doesn't condense and the heat doesn't get removed. So now you got a twofold problem. So now you've got vaporized refrigerant or hot gas coming out of that compressor right here, going through 0.6, 7, still not condensing at this point because your system's got an issue, and possibly not even condensing at all, and getting all the way to the liquid line as a hot gas or a partial hot gas. So now our TXV is not going to work right. So that's going to be impacted because it's not getting a full column of liquid. So that's an issue. Our compressor is going to have to work harder. Why is it working harder? Well, because it's trying to get rid of all this heat. So it's getting hotter and hotter and hotter. Pressure's rising up, up, and up. So if I'm not removing that heat, then where does the heat go? The heat's supposed to be removed through the fan, and it's supposed to leave the coils here in the condenser. If it doesn't, then it gets sent on to the next step, assuming that it's been removed, but it hasn't. So now I've got all this additional heat that I should have got rid of that now I'm going to try to send back through the indoor system again. So ultimately, your indoor system is going to be impacted by this as well. But the first thing that's going to happen is your compressor is going to start to work harder. Your amperage is going to go up, and your head pressure is going to go up. By head pressure, I mean your high side pressure on your gauges. So your gauges are going to start to climb probably pretty quick. This is where you'll probably trip out on some sort of high pressure limit hopefully if you have one. So your pressure is going to raise. Your subcooling is going to be pretty much non-existent or really low because you're not able to subcool because you're probably not even able to condense because you're not getting rid of any heat. Now, if this were a dirty coil instead of a completely blown fan, a dirty coil may still condense some, but your head pressures are going to be higher. You're not moving the amount of heat that it's designed to move. So yeah, you're moving some, and you may even see a little bit of subcooling, but it's going to be low. So in the event that you have like a really dirty condenser, it's moving all it can move, but just can't move enough, you'll probably see low subcooling. That low subcooling may allow everything else to kind of work okay, but when it gets really, really hot outside, that's probably when it's not going to keep up. So that would be the event of loss of airflow. So back to your picture, dirty condenser or poor fan or loss of condenser fan, your suction pressure is going to go up. Why is it going to go up? Back to the picture. So your suction pressure is going to go up partially because your TXV is probably not working right, but also the heat that we should have got rid of before we sent it back to the evaporator now isn't getting rejected. So now you're going to have this additional heat still in the refrigeration circuit, and you're still adding heat from inside the house. So as a result, your pressures are probably going to raise a little bit on your suction side, and that's going to ultimately affect your superheat a little bit. If you've got a TXV, that TXV is probably opening and closing, trying to kind of settle things out, so you may not notice it too much there. But ultimately, if it runs long enough, it's going to affect the inside too. But chances are you're going to notice it on the high side before you ever notice it on the low side. So let's go to the next one. Let's see, low indoor airflow or low return air temp. So low indoor airflow would be dirty filter, dirty evaporator coil. No indoor airflow would be loss of a fan, so your blower kicks out. Oh, by the way, dirty condenser is going to cause your delta to go down. Why is your delta going to go down? Because now you can't remove the heat you wanted to remove. So, instead of a 15 to 22 degree delta, you may have 12. So that would be another indication that you could have an issue there. So if the first thing you checked is your delta, you went in and checked delta before you ever put gauges on, and you're reading a 12 degree delta, then you'd go, I wonder what's going on. Go outside, put your gauges on, and you probably see high head pressure and then maybe higher than normal suction as well. So all those are going to point to that. And then you're going to measure that superheat subcooling to kind of help narrow that down, because you could look down through and you could say, well, if I'm only using pressures, so this is where people go wrong. They only use their gauges and they say, well, I've got high suction pressure and high head pressure. All right, so what things could it be? Well, it could be dirty condenser, it could be overcharged, and it could be a high return air temperature. All right, now you could eliminate a few of those just because it's maybe not overcharged and that it's, the inside temperature is fine, but that's three different things that it could be. Now, let's compare those three together. Overcharge, superheat's going to be different on it, possibly, than it is on dirty condenser. I'm looking at this one down here. It doesn't have dirty condenser. Yeah. Your subcooling is different. So on dirty condenser, your subcooling will be low. Overcharge, your subcooling will be high. So these things are all adding up to say, well, it can only be this, this, or this. Notice also your deltas, all these would be low in this case, so it's not going to be any different. But really, what subcooling does and superheat does is it starts to let you see the whole picture. So suction pressure, head pressure are great things to read. You should be reading those. But just those alone, most of the time, can't tell you all that you need to see to really be able to diagnose this. Now, some people would argue that and say, well, I can tell by feeling. But even by feeling those lines, they're taking superheat. They just don't realize it. They're saying the line's cold or the line's not cold, and that's telling them something. All right, so let's go to the indoor unit. Indoor unit, airflow, let's say you get a dirty filter. All right, so back to our little chart. What were the symptoms of low indoor airflow? Suction pressure would be low, and head pressure would be low to normal. Same thing down here. You come down here to a TXV system, and you can say suction pressure would possibly be normal. Why would it be normal in a TXV? Sorry, wait, I'm looking at the wrong one. It would be low airflow, not charged. Low airflow, it's going to be low. Head pressure is going to be low as well. Low to normal. Your superheat in both of those cases is probably going to be low. In a TXV, it could possibly be normal depending on how bad the restriction is. Your TXV is going to try to fix that, but it may not be able to. Subcooling looks pretty similar on both of those. Both of those will be low. Your compressor amps is both going to be low, and your delta is both going to be high. So not a huge difference on those two as far as TXV to fixed. So now what does that mean? So the first thing it says is your suction pressure and your head pressure are going to be low if you have low indoor airflow. So look through your table here and see what other conditions can cause you to have low suction pressure and head pressure. So this is probably the biggest thing to understand, and biggest thing superheat subcooling really helps you determine. If you look at this first two columns and you go to low indoor airflow and then you go up to low charge. So low charge and low indoor airflow can look really, really similar by just looking at a set of gauges. Now there's other factors. Obviously, if you go on over, delta is different on those, so that may be a deciding factor. But for the people that only use their gauges, I've seen people do this. I've done this myself. You start putting refrigerant in one because your pressures are low. It doesn't get any better, and now all of a sudden you've got other issues going on. So you don't want to start overcharging a system thinking that it's undercharged, but it's really easy to do because if you only use your gauge pressures, it's going to look like it's low. All right, so why does it look like it's low? Well, let's go back to our picture here. So where are we getting the heat from in the first place? It's coming from the house, through the return, through the filter, hopefully there's a filter, and into the coil. Assuming that everything's clean, we should have enough air and enough refrigerant that system is matched to the load. So that system is designed for that house. As long as it's getting the right amount of heat, it's going to do the right amount of evaporating, and then you're going to have superheat left over. If you got a TXV, that's going to even maintain that a little bit better and make sure that it's the optimal amount. But either way, you should have enough heat available to superheat this refrigerant before you get done. So what is poor airflow going to do? Why? What happens if I cut off the air or I slow it down? Well, just like in the outdoor unit, even though this is the cold side, this evaporator is picking up heat through the process of evaporating, but it can't evaporate unless it's picking up heat. So if I stop the flow or slow down the flow of heat, then I slow down the rate that it's boiling. Well, if I slow it down enough, I'm going to not evaporate completely. And when I get to the end of the coil, I'm still going to have some liquid left. That liquid's going to go to my compressor and could ultimately cause me problems. So in a poor airflow condition, my superheat would be low or maybe non-existent, depending on how low the airflow is. What would your pressure do? Well, it said your pressure would be low. So why would your pressure be low? Low pressure your pressure is on your suction and your head really is determinant of getting enough air across it to actually regulate everything and set it where it's supposed to be. So if I have it set for a certain size unit with a certain amount of refrigerant at a certain amount of airflow, and then I change any of those, so I change the airflow. Well, now what was supposed to work one way is now working another way, a different way, because it was designed to have X amount of air, and now you've slowed it down or you've cut it off. So airflow will make my pressures drop on my suction side. On my head side, it'll make my pressures go up, right? Because what are they doing? Well, on the suction side, its job is to absorb heat. If it's not absorbing heat because it's not getting any air, which is full of heat, then your pressures are going to drop. Your superheat's going to go down because you don't have any heat available to evaporate, let alone to superheat or to boil it all off. And so now you're going to be sending liquid back, and your pressures are going to drop to the point that your coil is probably going to get freezing or below. Once it gets below freezing, that water is going to stick to it, and it's going to start to collect ice really quick. This is where you get your freezing up, most likely, is usually airflow related. Not always, but usually. So we measure superheat by strapping a thermometer to the vapor line, suction line, and by measuring our pressures. So if I measure my pressures and my suction pressure is 30, then you'd say, oh, well, or my suction temperature, sorry, my suction temperature is 30 degrees, and I expected it to be 40 to 45. Well, then that tells me that my pressures are low, right? I don't care about what pressure is, but at some point in time, it comes back into play. So it's all based on that temperature. If I expected it to be 40 to 45 degrees saturation temp, and it's really reading 30, I'm low. My pressure is low. So you go back to your chart and you say, pressure is low. What all things can cause low suction pressure? These three things. Down here, a couple of things down here. So on a fixed, let's just stick it with a fixed metering device. Low charge, low indoor airflow, liquid line restriction. Not worried about the restriction right now. But the main two are these two, low charge and low indoor airflow. And you could have both of these at the same time, and sometimes that'll cause a problem too. Like what if you've got a dirty filter and you got a leak? It happens all the time. So you need to be able to figure out how to fight each problem individually. And so that may be where subcooling comes in or something else. So if you're low on charge, if you're low on airflow, your head pressure, depending on how bad it is, your head pressure may not struggle from it, at least originally. Now, if it runs long enough, think about it. If you go back to your system, if the evaporator's job is to pick up heat and the condenser's job is to reject it, if I'm not picking up any heat, then it's going to be really hard to reject it because I didn't pick it up in the first place, right? So eventually my head pressure could get low. It may stay normal because that compressor is still sitting there pumping. All right, so let's see, go back to that picture. All right, so what's another thing that's going to differentiate low airflow from low charge? Well, we haven't talked about charge yet, so let's go over to low airflow delta. Your delta at this point is going to be really high. Now, that may seem like a good thing, but this is one of those cases to where you would say you can have supply that's too cold. So if I'm looking for a supply or a delta that's 20 degrees, let's say I got 75 in the house, and I'm looking for 55 in the supply, and I'm reading 45, and that 45 kind of doesn't seem like it's blowing real hard. That may be another indication, just feeling a vent, doesn't seem like it's blowing real hard. 45 degree air may seem great, but that's a 30 degree delta. That's too much, because in order for that air to be 45, that means that coil had to be colder than 45. So I'm going to be risking freezing already. So that's an issue. If that delta is too high, you got to figure out why that is. You got to get more heat to that coil more than likely, because it should only be in that 18 to 20, 15 to 22 range. All right, so why do I go through all that with the airflow? So the symptoms of low airflow inside is going to be low suction pressure, low superheat, or no superheat. Now, let's compare this to charge. So go back to this same chart. Low charge. What does low charge mean? It means there's not enough refrigerant in the system. So this is a really common issue. Low charge and low airflow can get confused a lot, and it's really easy to misdiagnose this. This is why I use this one as an example, because I've done it. I went to a job one time and was actually putting refrigerant in the system. I was in a hurry, didn't go inside, and didn't take all my readings like I should have, and was charging it up. The lady stuck her head out and said, "Oh yeah, I was going to tell you, there's no air blowing in here." Went inside, the motor on the air handler was dead, and so then I had to recover that refrigerant back out. So I learned that the hard way. Low charge, suction pressure will still be low, right? So in low charge, you don't have enough refrigerant. In low airflow, you have plenty of refrigerant. You just don't have enough airflow to move the heat across it that it needs. So both of these are going to look the same, maybe identical on the low side. Head pressure. Head pressure is going to be low because, once again, there's not enough refrigerant in the system. So you just don't have enough to go around. Superheat will be, all right, look at the two. Low airflow, superheat was low. Low charge, superheat will be high. All right, so let's go to our picture and let's look. So in a low airflow, in a low charge condition, imagine that this dark blue column going through this coil is your liquid. Now imagine that we lose 30% of our charge, so we got a leak. Well, now all of a sudden you don't have as much refrigerant available. So if I don't have as much available, I don't have enough capacity to cool the house, especially when it's in a high demand. So now, instead of having 80% of my coil or 85% of my coil available to do all the work going through the latent change, now I'm going to run out way down here by like 0.15, this little point right here. That may be fine as long as it's not super hot and you're not trying to get rid of, all the heat that it could be asked to get rid of, like in in the middle of the summer. But once it gets hot, that's when it's going to struggle, because this evaporator is only operating at 50% capacity. Because remember that latent change is what's doing the work. So unless that thing's going through the latent change, it's really not doing anything. So this is a misdiagnosis or an easy misdiagnosis. And it's also a case where you would say, well, the latent change really matters as much or more than the coil being colder, because if you have a low charge situation, your airflow is going to be warmer than you want it to be. Your superheat's going to be warmer than you want it to be, but your pressures are going to be low. And so if you're just going by pressures and you say, well, if that's cold, then it's that's an indication of low charge, but at least it will cool really well. It won't cool well because most of that coil is superheated. It's already superheated, which means it ran out of refrigerant way before it should have. So only a part of the coil is actually doing the work. So now I don't have near the capacity to grab the heat and actually carry it outside. So if I have a low charge and I run out down here at like halfway through, then I only got half the coil doing the work. And so what's left, once it completely evaporates, what's left is superheat. So that superheat goes through the rest of the coil and it adds sensible heat. So instead of having 8 to 12 degrees of superheat, you may have 20, 25, 30 degrees of superheat. So now when you measure this line down here and you're measuring that and you're expecting it to be 55, let's say, you're reading a 70 degree line, a 65 degree line. So this is where, if you get used to just feeling things, if you walk up to that unit and it's running and that line is just sort of lukewarm or, cool, but not cold, it's not sweating, it's not really what you'd call cold, that may be an indication, most likely, that's an indication of charge. If your pressures are low and that line is not cold, more than likely it's charge. If the pressures are low and that line is really, really, really super cold, then it's probably an airflow issue. So, don't discredit people that kind of use those old-fashioned ways of doing it. I do that too. Like, if I stick my hand to that, I'm measuring superheat. I just maybe don't know the exact number, but that's what I'm doing. So when you measure superheat, you're measuring the latent heat change between the saturation point and that line, whatever that line, that line's going to get warmer. So once it superheats, we're going to be able to measure that temperature. with a thermometer, and that's why we just strap a bulb to it. Now, that's the same way your TXV works. It straps a bulb to that line, and it uses that bulb to help it know when to open and close. So low charge will have the opposite in superheat. Your pressures may be identical, and I may give you an example of that where your pressures are exactly the same, but your superheat is completely opposite. One of them's running under a 3-degree superheat, and the other one's operating under a 30-degree superheat. What's the difference? It's either charge or airflow. You got to decide which one. So the one with low superheat is going to be airflow, and the one with high superheat is going to be charge, most likely. Outside unit is affected by charge as well. So according to your chart, your low charge, your subcooling will be low, once again, because you don't have enough refrigerant, and your head pressure will be low because you don't have enough refrigerant. Your amperage will be low on your compressor because it actually doesn't have to work as hard because it's not pulling as much refrigerant through it. And your delta will be low. Why will your delta be low? Well, back to the capacity of the coil. If I'm bringing in 75-degree air and I'm wanting to cool it down to 55, I got to have this coil doing the most work that it can do. So if it loses some of its capacity and it's only working at 50%, now instead of a 20-degree delta, I may have a 13-degree delta. It may not seem like a huge difference, but it's a very huge difference because that house is designed that it needs to remove that much heat every hour. And if the system's not working right, it's going to run all the time trying to do what it's supposed to do. It's never going to satisfy. Your electric bills are going to be higher than they should be, and you're not going to be comfortable. You're also not going to remove as much moisture because you don't have as much coil removing the moisture. So everything just sort of starts to struggle in low charge. So that is a basic guideline. Probably the two most basic problems is low charge and low airflow. Low airflow outside, low airflow inside, and then charge affects everything. So hopefully this helps you at least get started. We'll be doing these in lab. So your lab 6A covers the airflow side, and you'll be simulating those by putting things in the block the airflow or whatever. The other one simulates the charge side. So I'll actually have you put in a little extra refrigerant and then take out some of the refrigerant. So in order to take it out, I'll give you some instructions on how to do this in class, but really all you're going to do is you're going to hook a recovery cylinder up to this liquid line, and you're going to open up the liquid line port and the yellow center port, and you're going to let the system push out so much of that refrigerant just out of the liquid line into the tank. So you're not going to use a recovery machine or anything like that. So we're just going to push some of it out, let the system push it out, and then we're going to put it back in and then maybe overcharge it just a little bit and see how that reacts. So have those labs ready, and we'll do those next time.